version of GCSE Chemistry, topic by topic. We're going to have a look at reaction profiles, and we're going to go on from that to have a look at bond energy calculations. Reaction profiles, let's have a look at these. What I've got is a simple reaction, and what I'm going to do is try and draw a graph of this reaction. What I'm going to have is along the axis here, we're going to have energy, and along this one we're going to have sort of a progress of the reaction. I'm going to start with our reactants, and they've got so much energy. Now when these start to react, they can either have an exothermic or an endothermic reaction. Let's look at an exothermic reaction, and when they finish we've got our products, and they have less energy than they've started with, so energy is lost. What happens to this energy? It needs to be given out to the environment. So this is an exothermic reaction, in that energy is lost to the environment. We've got another reaction that looks like this. But this is an endothermic reaction. So, much as the other one, we've got energy and we've got progress of the reaction. We start off with so much energy in our reactants, but at the end of the reaction our products need to take in extra energy. So this is an endothermic reaction, and it needs to take from the environment. I'll call it ENV for short. Now, reactions like this don't really occur quite like this, because let's look at an exothermic reaction, and I'm going to look at a fairly well-known exothermic reaction. And what we're going to have in this exothermic reaction is my reactants, and these are going to be carbon and oxygen. This is charcoal, this is oxygen from the air, and what I'm going to do is I'm going to do my classic barbecue. Now, if any of you have ever tried to get a barbecue going, you'll know that you don't put the charcoal in and put the oxygen in, and suddenly out comes lots of energy to make our products, which are in this case carbon dioxide. It just doesn't work. You can sit there for ages, but you can put the charcoal there and it just won't do anything. To get the system to work, we need to put some energy in, and then we get the energy out. This bit of energy here that we need to supply to get it going is called the activation energy, and we give it the symbol E for energy, A for activation. So this is our activation energy, or sometimes called the energy of activation. So we've got to put in some energy so that we can make more energy, and when that energy is being made, it's enough to get the rest of the reaction going. So once we've put this in, it's enough to keep the reaction going, so we only need to put it in once, and we get lots of energy out. So this is still an exothermic reaction. Also, we could look at another reaction. And we'll do it again. We'll put in our reactants, and because it's an endothermic reaction, we've got our products up here. Again, this is energy, and this is the progress of the reaction. I need to put some energy in, but not just enough to do that. Sometimes we need to still put in more energy than the products. So again, I've got this activation energy. So basically we have to think about this as here, just an endothermic reaction, but I needed to put in more energy. So we need to think about a definition of our activation energy. It is the minimum amount of energy that needs to be added that will actually cause a reaction. And it doesn't seem necessarily obvious that we need to do that, but it does. So we think of colliding particles. Unless the particles have enough energy to collide, then they simply bounce off. If they've got the required energy, then they can combine. And it's this minimum amount of energy, the energy of activation. We think about this as really two parts. Any reaction always works the same way. The reaction works first with bond breaking, and this is always followed by bond making. If we think about what's going to happen, let's take a very simple reaction. Let's take some hydrogen, and I'm going to get that to react with some nitrogen. Then if I want these to react together, what I've got to do is make sort of an intermediate step. I've got to break all those bonds before I can make them again. Bond breaking, bond making, and we get this sort of idea of having an intermediate here that probably doesn't exist, but we've actually had to break all those bonds, and that is going to release lots of energy eventually. But to do that, we've got to put energy in. So energy has to go in here to break those bonds. Energy is required before the energy can be released. So for this stage, we must put in some energy before we get a release of energy. And depending on which is greater, we have our endothermic and our exothermic. Of course, in reality, these two processes don't happen in sequences. You know, all the bonds don't break and then all the new bonds form. The bond breaking and the bond making processes happen at the same time. However, trying to compare the energy required to break the bonds with the energy released when the bonds form give us a good idea about this overall energy change. And you can look at various figures for these things and you can decide whether this is going to be an endothermic or an exothermic reaction. What I've got here is a little table of data, and here I've got a whole series of different bonds, and it gives me some relevant information about the length, but largely the thing is giving me an idea about the amount of energy in kilojoules per mole for breaking and making bonds. And here we're seeing that the energy required to break a bond should be the same as the amount of energy to make a bond. And this basically comes from this law of the conservation of energy. So you can't get out more than you put in. So what we can do is we can use a table like this to try and help us work out all types and manners of calculations. So let's have a look at some of these bond energy calculations. Let's start off with a simple substance like methane. So if I start with methane, I've got carbon and I've got 4 hydrogens. Now these 4 hydrogens we're going to join to this carbon to make methane. Now over the years people have done a whole series of experiments and they've worked out the amount of energy in just one of these bonds, and we're going to use the word average because this is very important. This is the average amount of bond in a CH bond, and this is 413 kilojoules per mole. Now, how do we get figures like this? Well, someone might do an experiment to remove one of those and it takes so much energy. Perhaps they do another one and it takes perhaps a bit more energy and a bit more and a bit more. And they repeat this many, many times and we come up with an average. So if we do the real experiment, we might find that this is going to be very slightly different. But it's only going to be slightly different because these are done many times, these averages, and so we've got some idea of what they are, and they're fairly accurate. Go from one book to another, you might find these numbers change a little bit, but not much. So I've got this energy. How many of these bonds have I got? Well, I've got 1, 2, 3, 4 of them. So I've got 4 times my CH bond. In other words, that's going to be 4 times 413. And using my calculator, then we can simply work out what is 4 times 413. 1652. Kilojoules per mole. So that is the amount of energy in a molecule of methane. Now if we look up what the value of burning methane is, this amount of energy to create our methane, this is calculated by me at 1652. But if we want to work out the energy for the formation of methane practically, we'll find that this number is very slightly different. And it won't be radically different, but it will be slightly different. And if we look at this in another chemical, we'll find the same sort of thing. If I look up the value of this, the energy here in methane, you've got me ethane. It's alright, my son looked it up for me to give me the values, and that's different. Entropy of formation. Right, we failed. We'll look up that one up and get that one in a sec. Let's look at ethane. If I look up ethane, what I've got is a different number. Let's see what bonds we have here. Well, I've got my carbon hydrogen bonds. There are 1, 2, 3, 4, 5, 6 of these. And I also have a carbon-carbon bond. And if I look up my carbon-carbon bond, here I've got 347. So my energy in this is going to be my 6 times my 413, and what I can do is, let's just do that. I was going to do it the easy way, but it didn't. 6 times 413 gives me 2478. So let's add those two together. And that gives me the energy in an ethane molecule to be 2825 kilojoules per mole. let's just have a look at a couple more of these chemicals to see what's going on. So let's look at a different chemical here, and this is carbon tetrachloride. This is like methane, except we've got 4 carbon chlorine bonds. So if I want to look up a carbon chlorine bond, then we simply take my little table, look up a carbon chlorine bond, 339. So we can work out how much energy is available here. So it's simply going to be 4 times 339, which gives me 1356. So this is the amount of energy in this particular molecule. If we change this molecule a little bit and we meet trichloromethane, then this will have the carbon chlorine bonds. There will be 3 times this, and I've got 1 carbon hydrogen bond, which we worked out was 413. So simply we need to work out what 3 times 339 is. And simply then add those together. And you can see that making these has different energies. Methane 1652, ethane 2825, a considerable move up. Methane, however, to our carbon tetrachloride 1652 to down to 1356, and by adding 1 extra hydrogen in there, then the energy goes up. So we've got some energy calculations. Now sometimes we get some slightly more complicated molecules. Let's just have a look at a couple of those, and we might get something like alcohol. So if I work out the bonds in alcohol, there is our alcohol. You might find someone would write that as C2H5OH. Sometimes you might see them write it as CH3CH2OH. But regardless, we've got to try to get this in this form so we can work out how many carbon hydrogen bonds we've got, how many carbon bonds we've got, how many carbon oxygen bonds we've got, and how many oxygen hydrogen bonds we've got. So we've got for this 1, 2, 3, 4, 5 of those, and that one we've already worked out. We worked out the carbon hydrogen bond was 413. We've got a carbon bond, 1 of those, and we worked out that was 347. But there we've got 2 new bonds, of which we've only got one of, a carbon-oxygen bond, and the carbon-oxygen bond comes out at 358, and an oxygen-hydrogen bond, which comes out at 467. Now it's a process of simply trying to work out what these are, and doing this is really quite simple. All I've got to do is work out my 5 times 413, and to that I'm going to add my 347, I'm going to add my 358, and I'm going to add my 467. And that's going to give us 3237. So there is a chemical like alcohol, ethanol, so we can work that out. If we had a slightly different molecule, and I'm just going to draw a slightly different one very quickly out, like this one, and this is a slightly different chemical. This is acetic acid vinegar, and it's got then a different type of bond in. We've got 3 times our CH, we've got now a carbon-carbon bond, we've got one of those, we've got one carbon double bond O, we've got one carbon single bond O, plus we've got 1 times OH. We've got all these figures here apart from this one, so this is going to be 3 times 413 plus 347, and we need to work out a carbon double bond. So carbon double bonded to oxygen is 745, and we compare that with a single bond, which is here 358. So you can see that a double bond has in fact got more energy in it than a single bond, and all we need to do is to add these up. Well, I'm not going to do that one because you've seen how to do that, so let's now move on to working out how we could use this, and let's look at a reaction. And we'll start off with something that is hopefully familiar to you, and this is where I'm going to take some hydrogen and I'm going to react this with some nitrogen, and I'm going to form a molecule of ammonia. And I know from doing this before that when I balance this I need 3 hydrogens, 1 nitrogen to form 2 molecules of ammonia. So what we've got to do is work out what bonds we've got on this side and what ones we've got on that side. So we need to supply in energy to simply break these bonds. So to break these bonds. We've got to break this hydrogen-hydrogen bond, and that is 432. But I don't have one molecule to break, I've got 3. And I've got a nitrogen-nitrogen bond, and this one is, as you might predict, much higher, because it's a triple bond, this one, at 945. So we can work out the amount of energy required to break the bonds, the amount of energy we require to put in to this reaction. So let's do the calculation. This is going to be 3 times my 432, and I'm also going to have to supply in the energy to break the nitrogen, which is 945. So I've got to put in a massive 2241 kilojoules per mole. Now, let's see what we're going to get out. Well, the bonds that we're now going to make are NH bonds. For ammonia, there are 1, 2, 3 of those. Let's just give you an idea that this is what ammonia looks like. So we've got our 3 NH bonds. My NH bond is 391, looking in my tables. But I don't have one molecule of this, I've got 2. So I'll need to multiply my answer by 2. Or if I do it all in one go, then simply we've got 6 times my 391. And that gives me 2346. So I've put in 2241 kilojoules for every mole, and I get out 2346 kilojoules per mole. So we're getting out more energy than we put in. So I've got my number, and I'm going to take away my 2241, my first number, and I'm getting out this 105 kilojoules per mole. So I'm putting in this amount. I'm requiring to make, we're going to need this amount. So to break the bonds, I've got to put in this amount of energy. When I make the bonds, we get out this amount of energy. So I've got here a surplus of 105 kilojoules for every mole. What happens to this? Well, this means this is an exothermic reaction. It is going to give out a small amount of energy. Let's take another substance and let's see what happens if we might like to try and play with this. So let's take a reaction, and the reaction I'm going to take is one of ethene plus bromine gas. Now this gas is probably going to be easier if we dissolve this in some water. So this is bromine water and ethene. Now this is the test for ethene, and what happens is we get a bromo ethane. The bromine reacts with the ethene and goes from brown to colourless, and later this is used in GCSE Chemistry as a test for the ethenes. Right, so the first place to start is to know what ethene looks like. It's got 4 times our CH bond, and we've got 1 times a carbon-carbon double bond. And I've also got to break up my bromine because I've got here 1 bromine-bromine bond. Let's look up what these numbers are. Well, they're not that difficult. We've already looked at some of the numbers in this chart and we've got some ideas of what they are. So our carbon-hydrogen bond is 4 times our 413. Our carbon-carbon bond, we've worked out, is 614. And I've also got 1 bromine-bromine bond, and this one isn't actually very high. It's only 193. So let's add up these and work out what we've got. So I've got my 4 times my 413, and I'm going to add to that my 614, and I'm going to add on my bromine, which is 193. So it means for this reaction I've got to put in 2459 kilojoules for every mole that I've got. Now, what's the substance we make? Well, we're going to make here bromoethane. What have we got? We've got 4 CH bonds, and we've got 2 carbon bromine bonds. Well, that's going to be 4 times 413, and my carbon bromine bonds here is 276. Don't worry about trying to remember any of these numbers. If they give you this in an exam, they will always give you the numbers that you need. So let's work this one out. So I've got my 4 times my 413, and I'm going to add to that my 2 times my 276. Two 2204. Let's take them away and see what happens. So I've got my 2459, and I'm going to take away my 2204, which was already as my answer, and I get simply 255. Let's look at what we're doing. We need to put in energy. We need to break these bonds. So we add 2,459 kilojoules for every mole of that substance. And we get out from this, when it makes the bond, 2,204 kilojoules for every mole that we've got. And if we look at these two, you can see that we are putting in so much energy and we're getting out less. We've got less energy. So what can we say about this 255? Well, we put in this amount of energy, but we only got out that amount of energy. So we're short of 255 kilojoules for every mole. So this is an endothermic reaction, and this will need to take in that amount of energy from the surrounding environment, and that means that this reaction is going to be cold. When you add this, it's going to be cold. Not very cold, because it doesn't require an awful lot of energy, but it's going to have a slight amount of energy taken from the environment. Let's look at one that's certainly going to give a bit of energy out to the environment, and this is a reaction that you do probably at home quite often, or if not there, in the lab. And let's take some methane and let's burn it. So I'm going to take some methane and some oxygen. Methane, we know, CH4, that gives me 4 of these CH bonds, so that's going to be 4 times whatever CH is, and we know that's 413. We've met that number many times before. And then oxygen, we need to break the oxygen, the O2 bond, and this one they've just written here as O2 is 498, and there's only one of those. But is there? Let's see what happens when we do this reaction. Well, my methane plus my oxygen, I've got then CH4 plus O2. What are we going to get when we react these? Well, I'm going to get the oxygen reacting with the carbon, this is going to form carbon dioxide, and I'm going to get my oxygen reacting with my hydrogen, forming water. For each methane molecule, we're only going to require one oxygen molecule, because that's going to make CO2. So I'm going to require just one of those, but for the water I'm going to require an additional 2 molecules. So we've got 3 of these in total, and that's going to give us one of those, and it's going to give us 2 of those. So that's going to be oxygen, that's going to be 2. So that's only going to be 2, isn't it? I got that wrong. I was not balancing my equation correctly. I was just doing it. So if we want to balance this, I've got 1 oxygen from there and 1 from there, so that's going to give me 2 of those. So that means I've got 2 down here. What molecules have we got here? Well, this is carbon dioxide, C double bond O, and there's 2 of those, so that gives me 2 times C double bond O. And I've got here an H2O. If I look at my H2O, I've got 2 OH molecules, but I haven't got 2 of them because I've got 2 molecules, so that's going to give me 4 in total. This is why I've got to get the equation to balance before we do anything else. So let's do our calculations. To do our calculations then, we've got my 4 times my 413, plus I've got my 2 times my 498. So a total amount of energy that I need to put in to break all the bonds, 2648 kilojoules for every mole. What do we get out? Well, I've got to work out my carbon double bond, and that is 745. So I've got 2 times 745, and my OH is 467. So I've got my 4 times my 467. Let's work out how much energy we're going to get here. So I've got my 2 times my 745 plus I've got my 4 times my 467, and I've got 3358. Again, kilojoules for every mole. This is what we put in to break the bonds. This is what we get out when we make the bonds. So let's do our sum, and our sum is going to be our 2648 minus my 3358, and it's going to give me minus 710. This is my kilojoules per mole. So it's negative. That tells us it is exothermic. So when we burn methane, we get out 710 kilojoules for every mole. Well, let's just look at another substance, and we're going to have a look at ethane. Now, ethane's not very different to methane. We've got this carbon-carbon bond as well. And I'm going to put some oxygen in there, and I'm going to burn it, and I'm going to make CO2 plus some water. Our first job is we've got to balance this reaction to work out what we require. So I've got 2 carbons on this side, so I must end up with 2 carbons on that side. I've got 2 for 6 hydrogens on this side, so I must end up with 6 hydrogens on that side. Let's count up how many molecules of oxygen this would be. So I've got 2 O2s, so that gives me 2 of them, and this is going to give me 6 O2s. That's not, you see, that's only going to give me here, if I got 6 molecules of this, then we're going to need 3 O2s to try and sort this out, but we're not. See, we've got this H2O, so we're actually, to get these 6 here, we only need 3 of these, because 3 2s make our 6, and that means we want awkwardly 1.5 oxygens. Oh, this isn't very nice, is it? So that's going to mean we'd want 3.5 on this side. Well, chemistry's not going to work very well like this, is it? So it would be better that I had 2 ethanes plus 2 lots of this, which is going to give me 7 O2s, is going to give me 4 CO2s plus 6 H2Os. Now we're ready to try and do our reaction. So what's ethane got? Well, ethane has got a carbon-carbon single bond, and we've got a carbon-hydrogen bond, and there's 6 of those. There's 1 of these, and I've got 7 lots of my oxygen bond. My results, I've got 4 CO2s. This is going to give me my carbon double bond. I've got 2 here in 1 molecule, so 2 4s are going to give me 8 lots of those. Plus I've got 6 waters. That is my OH bond, and I'm going to end up with 2 of those in each one, so 2 times 6 makes 12 times those. Now all we need to do is to work out these numbers. My carbon-carbon bond, 3 4 7, my carbon hydrogen bond 413, my oxygen bond 498, and then we're going to get my carbon oxygen bond 745 and my OH bond at 467. Now all we need to do is work them out. So to work those out, I've got my 6 times my 413 plus I'm going to have my 347 plus I'm going to have my 7 times 498. That gives us a whopping 6311. That's what we need to put in. But let's look at what comes out. I've got my, I'm just going to store that one. I'm just going to store that in the calculator's memory. And we're going to work out our carbon oxygen bond. This is going to be 8 times my 745 plus I've then got a massive 12 times my 467, and we get out a massive here 11,564. If we do the takeaway, and that's going to be then, I'm going to recall what I had in memory A, and I'm going to take away what's in my answer. We can see that we get minus 5253 kilojoules for every mole. And if you compare that with our values for methane, you'll see that we actually get out more energy. So it's worth heating, burning ethane compared with methane. We get more bang for our buck, more energy for our money. If we look at one more, and I'm not going to do this one, but I look at propane, then the difference between ethane and propane is that it's got simply an extra few bonds. It's got everything that it had in ethane, but in addition it's got an extra carbon bond and extra carbon hydrogen bond. So this is extra. So it's going to then give us out more energy than we had in ethane. So if you're using those little gas taps and got a Bunsen burner, it's going to give you out so much energy. But if you use a liquid petroleum gas such as propane or butane, then you're going to get out a lot more energy for the same sort of amount of fuel. in other words a mole. So we can get out more energy. So quite useful. These calculations then for working out bond energy calculations, I hope you can see they're not that difficult. As long as you've got a little table, you've got all the numbers, and in an exam question they certainly give you that. You would not be expected to remember any of those. So, not too bad. Hopefully this is useful, and you'll find that you can try some of these out and get some answers to some of these things. Later on in this series I will be starting to give you lots of questions on these things, so that hopefully will help you improve your GCSE chemistry topic by topic. So if you like this, please subscribe, give us a thumbs up, and I'll see you again next time when we do some more chemistry. Until then, stay safe, take care, bye bye.